Welcome to this explainer. Today we're diving into the absolute essential algorithm that practically runs modern automation. I'm talking about the PID controller. Whether it's dialing in the perfect temperature in your kitchen oven, steering a massive naval ship, or keeping a highly agile fighter jet completely stable in the sky, this exact algorithm is the invisible hand making it all happen. Our focus today is on the highly practical use of PI, PD, and PID controllers, and we're going to decode how they actually work out there in the real world.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the brains of automation, then meet P, I, and D. After that, we'll look at PI versus PD controllers, get into practical PID tuning, and finally wrap up with software implementation.
Section 1. The brains of automation. Replicating intuition. So, to truly grasp what a control system is doing, we have to recognize that these algorithms are, well, they're essentially trying to mathematically replicate human intuition and behavior. And to see where this all started, we have to look back at a seriously fascinating story from 1922. Russian-American engineer Nicholas Minorsky was designing automatic steering systems for the U.S. Navy. He spent a ton of time just closely observing how a human helmsman actually steered a ship. And he noticed something really important. The helmsman didn't just react to the current error in the ship's heading. No, they also considered past errors and exactly how fast the ship was turning. Minorsky literally translated this human intuition into mathematics. When they tested his theory on the USS New Mexico, the results were absolutely astounding. Adding that final D term resulted in steering that was actually better than most human helmsmen could ever achieve on their own.
That brings us to a really fundamental question. How do we replicate this human intuition in software? Well, think about when you're driving your car on the highway. If you hit an uphill incline, your speed drops, right? Your brain notices that error, and you instinctively press the gas pedal just a bit more. If the hill is steep, you press harder. But as you quickly approach your target speed of, say, 60 miles per hour, you ease off the pedal so you don't overshoot it. In that moment, your brain is acting as a highly advanced adaptive controller. Our goal here is to take that exact natural ability and turn it into a structured software algorithm.
Moving on to Section 2, meet P, I, and D, the three terms.
Now, what's really interesting about this slide is how clearly the architecture of the controller maps out. Let's break down these three distinct letters so we understand exactly what specific problem each one solves in our control loop. You can see our set point, basically our target, over on the left. We subtract our actual measurement to get the error. Then that single error signal is fed simultaneously through three entirely distinct mathematical paths. You've got the proportional path, the integral path, and the derivative path. Finally, they're all summed together to drive the process. Let's look at each one of these paths.
First up is the proportional term, or P. This handles the present reaction. It adjusts the controller output in direct proportion to your current error. So if you're really far away from your target temperature, the P term cranks up the heat. As you get closer, it lowers the heat. Simple enough, right? But there's a catch. If you make this term too aggressive, like if you apply way too much proportional gain, your system will wildly overshoot the target and begin to oscillate.
You can actually see that oscillation happening here. The process value is just fluctuating up and down around the set value. But even more critically, this reveals the main flaw of using a proportional controller all by itself. It almost never perfectly settles exactly on the target line. Because think about it, as the error gets closer to zero, the proportional output also drops to zero, leaving the system just slightly off target. This persistent, annoying little gap is what we call steady-state error.
To fix that steady-state error, we introduced the integral term, or I. You can think of this one as the solver for the past. It continuously sums up the error over time. Even if that steady-state error is absolutely tiny, the integral term will slowly accumulate it, gradually nudging the controller output until the error is perfectly eliminated and you are dead on target. However, it's definitely not foolproof. If a system gets stuck and just can't physically reach the target, the integral term will just keep building and building. That creates a really dangerous condition known as windup, which we have to manage very carefully in our code.
Finally, we add the derivative term, or D. This is our predictor for the future. The D term looks at exactly how fast the error is changing. If we're rushing toward our target way too fast, the derivative term acts as a stabilizing braking force. It decreases the output to prevent a massive overshoot. It's incredibly useful for fast-moving systems, but you gotta be careful. Because it looks at the rate of change, it is highly sensitive to any electrical noise coming from your sensors.
Section 3, PI versus PD controllers. Choosing the right tool.
Now that we know the key players, it's vital to understand that you don't always need to use all three layers at once. Depending on your practical application, sometimes a combination of just two is the absolute perfect tool for the job.
Let's contrast PI and PD controllers directly. A PI controller, using just proportional and integral, is fantastic for slow-moving thermal processes. Think of things like HVAC systems, flow control, or big industrial furnaces. In these setups, smooth, long-term regulation is the goal, and eliminating steady-state error is critical. On the flip side, a PD controller, proportional and derivative, is ideal for lightning-fast systems. We're talking robotics, drone flight, and motion control. In those applications, reacting instantly and minimizing overshoot is just way more important than worrying about a tiny steady-state error.
Comparing these directly side by side, PI perfectly eliminates steady-state error, but its overall response speed is generally slower. PD reacts incredibly fast and limits overshoot brilliantly, but it leaves that steady-state error completely unresolved. And of course, the full PID controller combines the best of both worlds. It gives you zero steady-state error, fast response, and minimal overshoot, provided you can actually tune it correctly. Section 4. Practical PID Tuning. Real-world steps.
So the crucial point is, it's one thing to understand the theory, but getting the controller to behave nicely with a real physical process is practically an art form. So how do we actually tune these parameters in the real world? Well, here is a highly recommended progressive tuning playbook used by actual field engineers. First, you increase your proportional gain for speed until you observe about a 15% overshoot. Next, adjust your integral time for robust control, essentially eliminating that steady error. Finally, if you actually need it, add a very small derivative time, usually about 1/10 of the integral time, just to stabilize the system. I really must caution you here. While a lot of textbooks teach purely empirical mathematical methods, like the Ziegler-Nichols rules, modern control engineers often find these result in very poor, overly aggressive practical results. The progressive, step-by-step method we're looking at here is much, much more reliable.
When you finally get it right, this is exactly what you're aiming for. The resulting output curve of a perfectly tuned controller gracefully reaches the target over time without wildly swinging past it. It really represents a perfect balance of speed and stability. But remember, at the end of the day, a PID algorithm is a linear controller operating in a totally nonlinear world. This means this perfect tune is usually optimized for a very specific operating point, like running at full load versus partial load.
Section 5. Software Implementation. Code for Real Systems. And this brilliantly illustrates the leap we have to make. Let's move from the theory of tuning on a graph to the messy reality of actually writing this algorithm in discrete C or C# code for a digital microcontroller. When you're coding for real physical systems, you must include these real-world safety nets. You literally can't just write out the pure math and call it a day. You must include a dynamic integrator or anti-windup to stop the integral term from accumulating infinitely if, say, a motor gets stuck. You absolutely must clamp the maximum controller output, because you don't want your algorithm commanding a fighter jet's rudder to just snap off, because the math asked for an impossible 90-degree turn. You need to apply low-pass filtering to the derivative term so high-frequency sensor noise doesn't cause totally erratic behavior. And of course, you must ensure your code updates at a fixed, proper sample time.
All of this leaves us with a rather provocative final thought to ponder. The PID controller was mathematically formalized well over a century ago by Nicholas Minorski, yet it still completely dominates modern industrial automation, robotics, and software control today. As highly complex AI and machine learning systems continue to evolve at breakneck speeds, will they eventually replace this century-old algorithm? Or is the PID controller proof that human intuition, our natural ability to observe, correct, and anticipate, has already been mathematically perfected? Thank you so much for joining me for this explainer. Keep analyzing, keep tuning, and I'll see you next time.